Hello everyone and welcome to another scientific video with the process operations, and today in this video we are going to discuss, can our moon hold an atmosphere or no? Can our moon hold an atmosphere or no? That's what we are going to discuss today. A burning problem for a physics student, right? Yes, of course. That's why today I'm going to answer this question. But first of all, I'm going to make the same request from all of you again. If you have not subscribed my channel so far, please do it, because this particular channel is little by little providing you the knowledge that you have been waiting for. Little by little, this particular channel is going to be one of the largest scientific blogging channels in the world. And let's move on to today's video. Can our moon hold an atmosphere or no? First of all, we must understand what is an atmosphere. Atmosphere consists of gas particles. Atmosphere consists of gas particles. Gas particles, when I discuss about gas particles, it's very important to discuss about their temperature. The temperature and the particle speed and the particles, because temperature is representing the thermal energy that the gas particles have. And in gases, we all know that the temperature, the thermal energy is not existing as thermal energy. The thermal energy is a form of kinetic energy that the gas particles have. And for kinetic energy, it's very important the particle mass and the particle speed. So at low temperatures, particles are moving with low speeds at low temperatures. At high temperatures, particles are moving fast with high speeds. That is the difference. So low temperature, low speeds. High temperature, high speeds. So this particular kinetic energy is represented by the thermal energy, and the thermal energy is represented by the temperature of the gas particles. Okay, now next one. The next most important thing is the escaping velocity. What is that escaping velocity? For any planet, for any moon, there is a certain thing called the escaping velocity. If you take any object and if you throw up, it will come down because of the gravity. If you increase the speed, what will happen? It will go further up and will come down because of the gravity. If you further increase the velocity, it will go further up and come down. But there is a certain velocity at which, if we throw up, it will never come back. It will escape the gravitational field of that cosmic object, a planet or a moon. So that particular velocity is called the escaping velocity. That fully dependent on the mass of the stellar object, the mass of the moon, the mass of the planet, or the gravitational field strength of that particular object. That's how the escaping velocity depends. And now we are going to discuss how to calculate the escaping velocity. Okay, let's say there's a stellar object, there's a planet or a moon, and there's a small gas particle, right? Now let's say a gas particle or any particle, no problem, right? Okay, now let's say the particle is moving this way with the escaping velocity. So it has two energies. First, it has the kinetic energy when moving. Then it has the potential energy due to the gravitational field. Due to the gravitational field. If it is the escaping velocity, it will go until the infinity without stopping. So at the infinity, it will stop. So at the infinity, the object will stop, and there's no kinetic energy. And at the infinity, there's no gravitational field because it's far away. Because of that reason, there's no gravitational and potential energy also. At the infinity, as the infinity is very far away, this particular gravitational field is not going there. So there's no gravitational field. So there's no gravitational potential energy as well. So at the infinity, as the object stops, no kinetic energy, as no gravitational field, there's no potential energy. So we can use the law of energy conservation. At the beginning, the gravitational potential energy is minus g m1 m2 divided by r, because the kinetic energy is in this direction, the gravitational potential energy is in this direction. So we have to put a minus. Then plus the kinetic energy is half m2 ve square. Ve means the escaping velocity. And at the infinity, there's no gravitational potential energy and there's no kinetic energy. So we can take this minus sign, minus part to this side. Half m2 ve square is equal to g m1 m2 divided by r. Gravitational potential energy is equal to kinetic energy. So m2 and m2 gets cancelled out, chuck blast. Then we have only half ve, the escaping velocity square, is equal to G m1 divided by r. R is the radius of the object, because at the radius you have the m2 particle at the beginning, and due to this distance the gravitational potential energy is greater. So r is the radius of the stellar object, planet or the moon. Now we can make the subject VE. VE can be made the subject. So VE is equal to 2g m1 divided by r square root. So this is the equation to calculate the escaping velocity. Now we can calculate the escaping velocity of moon using its own values. Okay. V is equal to 2 is to g. The gravitational constant is 6.67 multiplied by 10 to the power minus 11, and the mass of the moon is 7.35 multiplied by 10 to the power 22 kilograms, and the radius of the moon is 1.7374 multiplied by 10 to the power 6 meters. Finally, after calculating this, you will get the escaping velocity of moon as 2375.5841 meters per second. So that is the velocity that has to be achieved by any gas particle to escape the gravitational field of the moon. Okay. Now it means the maximum temperature that a gas particle can get is this one. The maximum velocity for any gas particle to get on the moon is this one. Otherwise, it will escape from the gravitational field of the moon. Okay. Now this one is a higher value. Some particles are moving fast, some particles are moving slow. So there must be a moderate value which fits for all. We call it the VRMS, or the root mean square velocity. How to get the root mean square velocity of this is divide this value by root 2. Divide this value by root 2, you will get the root mean square velocity which fit for all molecules. Now we are going to calculate that one. So take this value 2375.5841 meters per second and divide by root 2, you will get the VRMS, the root mean square velocity, as 1680.40 meters per second. Why are we taking the root mean square velocity? The reason is our gas equations are giving a moderate value for all particles. The gas equations are assuming that all the gas particles are traveling with the same speed, the same moderate speed. That's why we are taking a moderate value, root mean square velocity, and we are going to apply in gas equations. Okay. Now after calculating the root mean square velocity, now we are going to apply in gas equations. nRT is equal to 1 by 3 nmVRMS square. N is the number of moles of the gas. R is the universal gas constant. T is the absolute temperature of the gas. 1 by 3 is 1 by 3. N is the number of gas particles. M is the mass of one gas particle, and VRMS square is the square of root mean square velocity of gas particles. Okay, now after taking number of moles means mass total divided by molar mass. Mass total divided by molar mass. R is R, the universal gas constant. T is T, the absolute temperature of the gas. 1 by 3. Again, number of particles multiplied by particle mass means again mass total mass. Then again VRMS square. Now we can see M total, mass total, and mass total getting blast cancelled out. Right? Finally, T is equal to molar mass of the gas, VRMS of the gas, the root means the velocity of the gas square of it, and divide by 3 times universal gas constant. Now we are going to apply this value for a certain gas to calculate what will happen, what will be the temperature of the gas to stay on the moon as an atmosphere. Now first we are selecting nitrogen, because nitrogen is the most abundant gas that we have on Earth. So can we have nitrogen? We can have nitrogen as the first test. Okay, T. Nitrogen molar mass is 28 grams, means 28 multiplied by 10 to the power minus 3 kilograms. We can apply it here. VRMS, we have calculated here. We can apply this value 1680.40 and square root. Divide by 3 times the universal gas constant is 8.314. Now we can, after calculating this part, we can take that the temperature should be of the maximum temperature that the nitrogen can get on moon is 3175.29 Kelvin. That is the absolute temperature. But if you convert this to Celsius temperature, you can deduct 373 from it and you can take it. So the maximum Celsius temperature that the nitrogen can get on the moon is 2902.29 Celsius. That's comparatively a high temperature. Now we can understand, can moon bear an atmosphere or no? So if any nitrogen molecule want to escape the moon's gravitational field, the nitrogen molecule has to achieve this much of a high temperature. Nearly impossible. Actually, with the help of solar radiation, the nitrogen molecule can't take this particular high temperature. This can't be achieved. But why then moon does not have an atmosphere? So under this condition, moon can have an atmosphere. But at the real life, we can't see an atmosphere of moon. Why is that so? Actually, the reason is at the beginning. At the beginning, moon was also a hot melted ball of rocks, same like the Earth. That time, moon's surface was much hotter than this. So that is the time moon has lost its atmosphere. Not now. So if we want, today we can create an atmosphere for moon, but we have to pump at least about 20% of gases that we have in the Earth's atmosphere to moon to create that atmosphere. Otherwise, mathematically, scientifically, according to physics, moon can bear an atmosphere because until 2902.29 Celsius, the gas particles are not going to achieve the particle speed to escape the gravitational field strength of moon. They are not going to achieve. So moon can bear an atmosphere, but the problem is at the beginning moon was more hotter than this, and the atmosphere of the moon has lost at the beginning. That's why it doesn't work. Earth value is much bigger than that. That's why still in Earth we have an atmosphere. Earth value is much bigger than that, about 10,000 or 11,000. So at the beginning, Earth was also about 4,000 degrees Celsius temperature. So that time, Earth was holding the atmosphere because its gravitational field strength was more than that, bigger than that. It could hold. So that's why we are lucky enough to have an atmosphere. But Moon at the beginning, it was not lucky enough to hold an atmosphere because the temperature at the beginning was much higher, not to hold any gas particles on it. So, final conclusion is the moon can have an atmosphere. But the problem is, at the beginning, the moon has lost its atmosphere because of the hot conditions at the beginning. Okay, another problem was solved. Thanks for watching. If you like the video, please put a like. If you like the video and if you have to add something, you can put a comment. And if you like the channel, please subscribe. And let's meet again with a valuable scientific content like this in the next video soon. And thank you very much for watching the video. Thank you very much again.